Okay, this is a section on what we're going to call the squeeze. Theorem. Now, this is something that we're ultimately going to accept without proof, but it's pretty easy to grasp if you see it. So I'm going to need three functions, f, g, and h, and they all have to be continuous on an open interval a, b. So they don't have to be continuous everywhere, but they have to be continuous on a, b. And for every x on that interval, a, b, we're going to have it so that f of x is less than or equal to g of x, which is less than or equal to h of x. So if you kind of think about what's going on here, you've got, let's put this in the first quadrant. I have some x, I have an interval AB, and I have three functions. I have one called f, I have one called g, and I have one I'm going to call h. So h is the red one, the orange one is g. So I have these three functions. And on AB, so at least on this interval, f is above g. Oops, let's fix that. We're going to call this one h. We're going to call this one f. Sorry about that. So g is above f. There we go, that's better. And h is above g on that interval. So sorry about the mislabels, but we fixed it. We're good. All right. So if that's the case, and oops, we're going to call this C here. And there exists a C also on that interval, AB, where the limit as x approaches C of f of x is equal to the limit as x approaches C of h of x, okay, which we're going to call L. So as I get close to C, h is going to the same value that f is going to. If that's the case, then the limit as x approaches C of g of x, yep, you guessed it, has to be L. So if I can sandwich the function g between the h function and the f function, and at some point C, h and f have the same limit, then the limit of g has to be L. Now, this seems fairly obvious, and it seems like it's straightforward, and we're not going to do any proving of it because it would just be a tedious proof that doesn't give us anything that's instructive. But this helps us with some earlier problems that we've had. Okay, so we gave you before three limits that you had to memorize. And one of them was the limit as x approaches 0 of sine of x over x is equal to 1. Now, we're going to build a bit of a diagram here. Okay, so I'm in the first quadrant, and I'm going to draw a piece of the unit circle. So radius 1, radius 1. Okay, and what we're going to do is we're going to throw out a segment here to a point D going through that circle, and we're going to call this out here point B. Okay, and that's going to make a right angle. Okay, so this is going to be my angle measuring x. And then I'm going to drop in here an altitude there at point C. And we're going to note some things. Since this is the unit circle, this has a length 1, right? If this has a length 1, then we get some interesting things here. This is a right triangle, right? So the tangent of x has to be the opposite over the adjacent, which means that this has to be the tangent of x. So dB has to be the length of tan x. If I try to figure out sine of x, right, sine of x has to be the opposite over the hypotenuse. So remember, this segment right here also has to have a length 1, which means that this segment inside has to be the sine of x. All right, so this is the drawing that I'm working from. Now, from that drawing, I'm going to establish, that's a little yucky. Let's try that again. From that drawing, I'm going to establish some stuff. Okay? This is the tricky bit. The area of triangle, so we're going to make this point down here point A, CAB. So we're going to actually draw this over to here. So the area of triangle CAB, so that's the inside there, has to be less than or equal to the area of sector CAB. So that's, CAB is the triangle with the straight line, the sector is the curve, so that space between the straight line and the curve is the difference in the two areas there. So the sector has to be larger, and this has to be less than the area of the triangle DAB. Okay, so let's work this out. The area of this triangle is, well, it's its base, which is 1 times the sine of x. So it's half base times height, right? Half the base, which is 1 times the sine of x, its height, divided by 2. So that's the area of triangle CAB. The area of the sector, so let's think this through, okay, is going to be x over 2 pi, right? Because it's that portion of the circle, times pi times the radius squared. So the radius here is 1. So it'll be x over 2 pi times pi. And then the area of the big triangle is going to be its base, which is 1 times its height, which is the tangent of x, divided by 2. Okay, so clearing this up a little bit, this is sine of x over 2 less than or equal to x over 2 less than or equal to tan x over 2. Okay, so we're going to do something here. We're going to flip it all over. This means that 2 times the sine of x is greater than or equal to over x is greater than or equal to 2 over the tangent of x. Okay, if I multiply through by sine of x over x, so I'm going to multiply through by the reciprocal of this. So that's going to make this 1. Multiplying through by sine of x, over 2. Sine of x over 2, I'm going to multiply the reciprocal of that, is going to give me sine of x over x. And then, let's see, sine of x over 2 is, the 2's are going to cancel. Gives me sine of x over the tangent of x, right? Sine of x over the tangent of x. Tangent is sine over cosine, this is going to work out to be the cosine of x. So if you need a minute to see that, kind of work that out. Okay, so what we're going to do now is we're going to take limits. The limit as x approaches 0 of 1 is 1, right? The limit as x approaches 0 of the cosine of x, well, the cosine of 0 is 1. This means, by the squeeze theorem, that the limit as x approaches 0 of the sine of x over x also must be 1. 1, 1, 1, because this is a continuous function, that's a continuous function, that's a continuous function, everywhere but 0, right? But the limit exists at all three of these places, and I've got my game here. All right, so that is how we prove that limit. So now we can trust this, right? We've proven it. Okay, so what about the other ones? Well, we have good news. This one, the limit as x approaches 0 of cosine x minus 1 over x is equal to 0 directly follows from what we just did. So if I start with this, I get the limit as x approaches 0, cosine x minus 1 over x. Okay, so we're going to multiply top and bottom by the conjugate of the numerator here. It's going to be interesting here. So we get the limit as x approaches 0 of cosine x minus 1 times cosine x plus 1 over x times cosine x plus 1. Okay, so why did we do that? Because that creates a difference of perfect squares and gives me the limit as x approaches 0 of the cosine squared x minus 1 over x times the cosine of x plus 1. Okay, so why does that matter? All right, well, because I can do some breaking things apart here. If you think about this, right, so thinking sine squared x plus cosine squared x has to equal 1. We know that identity. So the cosine squared of x must equal 1 minus the sine squared of x minus 1 over x times cosine x plus 1. If you look, those ones fall out. So I just get negative sine squared of x over x times cosine of x plus 1. Right, so this is still a limit as x approaches 0. All right, so I can break this apart. I now have the limit as x approaches 0 of, well, let's see, negative sine squared of x can break into the sine of x times the negative sine of x, and the bottom can break into x and cosine x plus 1. Alright, so let's think about what happens here. This, we just proved, goes to 1. This is going to be 0 over 0 plus 1 is 1. 1 times 0 is, or sorry, 1 plus 1 is 2. Okay, so we've got 1 times 0 then is 0, which is what we tried to prove, that this limit through a chain of equal signs and some mathematical manipulation gets me to 0. But we needed this fact first, right, that this goes to 1. All right, so the only other one that we had to memorize was the one that involved e. Okay, so the third limit that you had to memorize was that the limit as x approaches infinity, so note the infinity, not the 0, of 1 plus 1 over x to the x is e. Euler's constant, right? All right, so why do I need this? Or what can I do here? Do I have to prove this? No, I don't have to prove it. No proof. Why? Because this is a definition. We define E as being the limit as x approaches infinity of 1 plus 1 over x to the x. Now, that's a definition, so that's what E is. There's no need to prove anything. You need to know it because we need to know this definition because it comes up. Okay? Now, one thing to recognize here. So there's a little bit of hand waving on this because we have to prove that the limit exists. Okay? Now, we have not proven that, and that is not part of this course, okay? So someplace later in mathematics, if you keep going, you will see a proof that this exists, but it's not part of our calculus course. All right, so squeeze theorem. One function sits between two others. You can get an indirect limit from that. We use that to get the limit that x approaches 0 of sine of x over x is equal to 1. We use that to get that the limit as x approaches 0 of cosine x minus 1 over x is 0. And finally, we've established that E is the limit as x approaches infinity of 1 plus the quantity 1 plus 1 over x to the x is E. Okay, so thank you.